Mark Friedel is a professor of geography at Boston University, and I've known Mark for God knows how long. He started his career in energy balance, if I remember right, and moved on to Moody's products. He has been in charge of producing Moody's product land cover, and he still survives after all the classes that he took. But more importantly, that he started this phenology work about 5-6 years ago, which is quite fascinating actually, because phenology from remote sensing has been probably one of the most challenging. So for him to go from land cover, which is already challenging, to phenology, it took a lot of guts. But today, he's not going to be focusing a lot on the satellite part of it, but he's going to talk about something that is even more interesting, in the climate phenology connection. And particularly his work that he has been doing with the Harvard Forest.
Yes,
yeah. And I think it really fits this workshop because we're trying to promote Earth observations for climate science. So it's kind of a broad topic, but there is no other topic that actually relates the two better than phenology. With that, Mark, how goes?
Great. Thank you, Rama. I actually know exactly how long we've known each other because we first met when you came to visit Boston.
Yeah, I stayed.
My first semester at Boston University, and Rama showed up in February, thinking that Boston would be a nice mild climate compared to Montana with no winter coat.
Yeah, right.
So we got through it. So it's been about 20. It was 1993. So it's been over 20 years. Time flies when you're having fun. Anyway, thanks for having me. It's nice to be here. What I'm going to talk about today is some work that I've been doing. Well, as Rama said, I've been working on this general topic for about, it's probably longer than 5 or 6, it's probably closer to 8 years. But what I want to try and talk about is some work we've been doing over the last couple of years, specifically looking at phenology, which is the seasonality of particularly temperate forest systems in the northeastern United States, in response to variability and change in the climate system. And how we measure that and really characterize the sensitivity of these systems to climate variability and change. Just before I get started, I do want to acknowledge co-authors on this. Josh Gray is a postdoc with me at Boston University. Eli Malas is a PhD student with me. Andrew Richardson is a colleague over at Harvard in organismal and evolutionary biology. We work quite closely together on some of this stuff. Trevor Keenan was a postdoc of Andrew's. He's now down at, I always say this name, Macquarie University in Australia incorrectly. And then I also want to acknowledge that the support for this has come from a mix of sources, including NASA, USGS, where else? NSF on a macrosystems biology project. And also I spent a year at Harvard on a fellowship, Bullard Fellowship, so I want to acknowledge their support. Okay, so I'm going to start out just talking a little bit qualitatively. These are some pictures I took last year out at the Harvard Forest. This is the new walk-up tower. Oh, I can't use this laser pointer. This is the new walk-up tower, which is replacing the old walk-up tower, which was formerly right here. This is the Neon Tower out at the Harvard Forest, which is you can see it here quite clear on this nice screen. It's a big structure. It's substantially larger than the older ones. And I think looks like about 5 stories above the forest canopy. So we're looks like southwest. So these pictures were taken up on top here. And basically what you're getting a picture of is the type of system I'm going to be talking about today, which is a hardwood deciduous forest in the sort of northeastern United States. Harvard Forest is a little bit different because it's a transitional zone between oak hickory to the south and sort of more northeastern hardwoods to the north. But by and large, this is the kind of system we're looking at. The other thing you can see here, if you look really close, this is the new Neon Tower, as I said. Over here, right here, is the EMS Tower at Harvard Forest, which is unique in the sense that it is the longest continuously running eddy flux site on the planet. So we've got, and long in this sense is not particularly long, but it's long relative to most records. It's 20-odd years of eddy covariance measurements, measuring biosphere-atmosphere interactions. And so just by way of kind of motivating this a little bit, I'm sorry, I tend to walk back and forth, so you'll have to be a bit patient with me. What I want to show you here, just to sort of maybe tease you a little bit on some of the things I'm going to be talking about, is daily GEE, Gross Ecosystem Exchange. The red line is 2010. The blue line is daily GEE from the other years in the data set. And so what, hopefully you should be able to see from this is that 2010 was an extremely unusual year, particularly in the spring. We had a very warm spring, leaves came out exceptionally early, and that drove a lot of kind of unusually high productivity throughout much of the season at the forest. Okay, so one of the things I want to sort of focus on is this notion of not just looking at trends in climate and ecosystem responses, but also this notion of trying to use unusual events in the climate system as precursors of what we might expect in the future. And so in this sense, 2010 is a good example. All right, so what I'm going to do, this is sort of the outline for the day. I'm going to give kind of a bit of a long, admittedly long introductory overview of the basic context here, just to set this up. And then I'm going to talk about three kind of distinct analyses which follow a parallel theme. I'm going to talk about this one thing which I affectionately call a tale of two springs at Harvard Forest, looking at a couple of unusual years, in the Northeast, using data from MODIS. But the MODIS record is only now 13, 14 years long. So now I'm going to take a somewhat longer view and look at 2 decades of in situ measurements of phenology in response to climate variability at Hubbard Brook and Harvard Forest. And then I'm going to take a step even longer time scale, slightly longer, and use the Landsat record to move backwards through 3 decades. And then I'll wrap up with some concluding thoughts. All right, so here we go. Phenology. This is something, particularly when you live in the northeastern United States, highly temperate, deciduous areas, that we kind of take for granted. But it's really a remarkable phenomenon. So this is a colleague, Nathan Phillips, former student of mine, Manish Verma, who's now down at JPL on a postdoc, at a field site in southern New Hampshire we used to work at. Okay, so this is a picture that I took in mid to early April, same location 3 weeks later. Right. So just qualitatively, it's an enormous transformation in the surface of the Earth. The microclimate, ecological environment, all this green stuff represents CO2 that's been pulled down from the atmosphere, the boundary layer of the atmosphere gets affected, and so on. So over a relatively short period, a remarkable transformation in the surface properties and conditions. All right, here's another example. This is from a webcam, so colleague Andrew Richardson, this is from our macrosystems biology project. Andrew has set up a network over the continent, primarily in the US, but we're building it out elsewhere, of webcams, he calls them phenocams, pointed at canopies. And the challenge there is trying to extract information from the phenocams related to phenology. So this is also at the Harvard Forest, so you can see if I go back, sorry, I'll try to, it's on the tower and it's sort of looking up over here, that's little Prospect Hill at the forest. Okay, so this is April 20th in 2012. That's the same date on the Boston Common, 65, 70 miles east. All right, so you can see the difference. Not much happening. There's a few flowers coming out in the oaks and maples, this kind of stuff. 60, 75 miles away, enormous difference. So on the first slide, we see pretty rapid changes across a short time period within season. In this case, we're seeing pretty dramatic changes over short spatial scales in response to subtle differences in the climate. There's an urban heat island, there's a coastal effect, and so on, but pretty remarkable differences. And then this is yesterday, basically the same date, but this year. All right. So we see big differences within year over a short period of time, big differences within year over short spatial scales in response to subtle differences in climate regime, and then big differences from year to year based on year-to-year variability. It's been a cool spring in Boston. All right, so I mean, there's this sort of, the main point here is that this forest phenology, they're responding to integrated forcing of the climate system, the trees and the canopies are. So they're a good diagnostic, they're a slow integrator of what's happening with the climate system. This is from work by Lizzie Wolkovich, who actually just started a job at Harvard. And she had a nice paper in Nature a couple of years ago in 2012. What this is showing is she did kind of a meta-analysis of phenological observations. The red dots are from warming experiments. So I can't use my... The red dots are warming experiments. The blue dots are just from historical records that have been acquired opportunistically. These are all data. These are data for which the species are the same in the warming experiments versus the rest of the data. And you know, one of the key results from this paper is that warming experiments don't replicate what we see outside of warming experiments, which is just a statement on how hard it is to do warming experiments, particularly with phenology. But the bigger point I want to make with this slide is just that this sensitivity, which is basically showing you the number of days change in the timing of flowering or leaf emergence for every degree change in the climate system. 1 degree change. Every degree we're getting 5-7 days earlier spring. Right? So what we've got a warming planet, and we've got a biosphere that's responding. All right, so this is work from Heather Graven, who's at Scripps, and this showed up in Science last fall-ish, I'm going to say. And this, I thought this was kind of a remarkable paper. I don't know whether you guys are familiar with it, but if those of you that are, just forgive me for going through this. But it's really, I think, really kind of an amazing result. What they did was they took aircraft data that was acquired circa 1960, International Geophysical Year, atmospheric CO2 mixing ratios, collected at 500 millibars, so roughly 6 kilometers in the atmosphere, and 700 millibars, about 3 kilometers in the atmosphere, over transects, right? And they compared that to pole-to-pole measurements via aircraft that were collected circa 2009 to 2011. So basically a 50-year span. All right, so what do you see from this? Basically what you see in over different 10-degree latitudinal belts. All right, so the black dots were collected around 1960. The purplish dots are from roughly 2010. And so what you can see is over this 50-year period, the amplitude, the seasonal amplitude of the northern hemisphere atmosphere mixing ratios have increased by as much as 50% over a 50-year time period. All right, so that's what this is kind of. This is sort of showing you the amplitude at different latitudes in 1958-63 versus 2009 versus 2011. So something pretty intense is happening. This is Inez Fung wrote a sort of perspective piece in Science about this, and she referred to the northern hemisphere hyperventilating, biosphere hyperventilating. So clearly, some big stuff is happening in the northern hemisphere related to the ecosystem response to climate warming. The challenge with respect to phenology, and phenology is part of the story, right? Longer growing seasons, that's sort of the easiest part to understand, is that remarkably, mechanistic understanding of phenology is deep, but does not predict very well. All right, so this is work from Andrew Richardson. This is part of the North American Carbon Program synthesis work that was published in Global Change Biology a couple of years ago. And what Andrew did, among other things, was he compared how models, so these are all these different biosphere models on this axis, reproduced phenology, and how those errors in those phenology propagated into estimates of net CO2 uptake. Right? And basically what he showed was, I don't want to be too negative, but the models are pretty bad. I mean, they're initiating leaf out anywhere from 2 weeks to 2 months before what they saw on the ground in these analyses. And what that leads to, particularly this is deciduous broadleaf forest, this is evergreen needleaf forest, these are the biases that leads to with respect to net carbon uptake. Strongly biased, so the models, just by virtue of phenology, they're taking up too much carbon. All right, so and this just reflects the fact that even though this is one of these things that people have observed and studied for centuries, we still really actually don't know how to model phenology all that well. All right, so then this is the last kind of contextual introductory slide, but I wanted to show this because I think it's actually a very powerful way of illustrating what may be coming down the pipe in the coming decades in New England. So this was a study that was conducted by the Union of Concerned Scientists, where they looked at climate change in the northeastern United States. And basically for different locations, this is New Hampshire, upstate New York, tri-state region, eastern Pennsylvania, western Pennsylvania. What this is showing is how the climate of New Hampshire, each of these guys, is going to look like by the end of the century under low emissions versus high emissions scenarios. All right, so the red ones are high emissions scenarios. So let's just take New Hampshire. Under a high emissions scenario, and this is based on IPCC fourth assessment report scenarios, if things go as the model suggests, the climate of New Hampshire summertime is going to be equivalent by the end of the century to what we now have in North Carolina. All right, it's a pretty big change. Upstate New York, you're looking at South Carolina, Georgia. Tri-state region, you're looking at South Carolina, Georgia, and so on. You get the picture. It's an enormous change coming down the pipe, and clearly these changes will have substantial impacts on ecosystems. All right, so what I'm going to sort of try and walk you through is some work we've done focusing on phenology, focusing on spring phenology in the northeastern United States. Kind of three main questions. What's the sensitivity? Like, can we actually develop simple metrics that quantify how much change we expect to see based on a certain amount of data? Secondly, and this is kind of a big one, can we use extreme years, unusual years, as kind of surrogates for what we might expect in the future? Instead of just looking at the trends, let's see if we can exploit some of these unusual years. And then lastly, I'm going to look at a variety of different data sets, and do we see the same type of story across these different data sets? All right, so I'm not going to go into a lot of technical details. This is kind of the extent of the way I'm going to explain the data. You're just going to have to. You should never trust anyone that says trust me, but you're going to have to trust me on this, right? So I'm going to be looking at in situ measurements of phenology. It's remarkable. There's not a lot of good ground data for phenology, particularly on time series, but two that we do have were collected at the Harvard Forest and Hubbard Brook. So we've got about a 20-plus year record at Harvard Forest. This is John O'Keefe, who's kind of the, I don't know, avuncular father figure of phenology in the northeastern United States. John just, he had the foresight 24 years ago to start, during his lunch hour, start collecting these measurements. He's been doing it himself for over 20 years now. And then Amy Bailey does the routine measurements up at Harvard Forest, so I'm greatly indebted to those guys. So I'm going to be looking at those measurements. I'm going to be looking at in situ surface meteorological data from two sources. One is the Harvard Forest and the other is the Hubbard Brook. And I'm also going to be looking at NOAA co-op stations throughout the northeastern United States. And then lastly, I'm going to be using remote sensing from MODIS, for which we have, I need to update this slide, so now we're up to 2014. And then Landsat, although the data I'm going to be looking at only goes to 2012, and then Landsat 1984 to 2012. And we're going to be just looking at simple metrics based on VIs, Enhanced Vegetation Index, that characterize phenology. All right, makes sense? So far so good? All right. So, one last sort of introductory thing before I sort of slide into the analysis. What I'm going to be doing, particularly in the context of looking at sensitivity to climate change and phenology, is using this notion, this is a very old idea, very simplest possible representation for temperate systems of what drives phenology, and that's this notion of growing degree days, all right, which is very simple. All we're doing is we're taking, for a fixed starting date, for which I use March 15th for the northeastern United States, we're accumulating temperatures above some base for which I use 5 degrees Celsius. So any day where it's above that base temperature, we're taking that daily mean average, we're taking the difference between that average temperature and the base temperature, and we're just accumulating. So these are cumulative thermal units, which are what the plants are responding to. And what I'm going to be looking at is anomalies in both the timing and the amount of thermal forcing. All right, so just sort of schematically to illustrate this green line, and this is just made up. I didn't even use real data to do this, at least for the long-term mean. is, let's just imagine that that's the long-term mean and growing degree days is day of year on the horizontal axis. So day of year 120 is roughly May 1st, right? And so 2010 was a warmer year. We had green up earlier. So we had a negative anomaly in the timing of green up and a positive anomaly in the amount of thermal forcing. It's warmer. And then 1997, which was a cooler year, we had a later leaf out. So we've got a positive anomaly in the warming, in the thermal forcing, and a negative anomaly, excuse me, a positive anomaly in the timing and a negative anomaly in the thermal forcing. All right, so I'm going to be looking at anomalies in each just to get you ready for this. All right, so I'm going to start with this thing I call a tale of two springs. All right, so this, what I'm showing you here is a map you get right off the NCDC National Climate Data Center website, which shows you for each state the rank in terms of overall temperatures from March through May in any given year. So this is 2010, and what you can see is in 2010, throughout the pretty much the northeast quadrant, but particularly in the extreme northeast, we had out of 116 years on record, the warmest spring on record. Okay, so which, you know, for me in the field I'm in, this is kind of a gift, right? It's a gift from nature in terms of sort of thinking about how to sort of prognosticate what's going to happen in the future. Just to sort of as an embarrassment of riches, 2 years later, and I'm sure some of you remember this, we got an even more unusual year, right? So here's the same thing, but we can see basically the entire eastern two-thirds of the country, once again, warmest on record. So now we're at 118 years, warmest on record. Again, eastern United States, but even extending further west. So now we have these two, in a relative sense, extremely unusual years for studying what's happened to phenology. All right, so what we did, starting out with just looking at data from MODIS, we took, I'm trying to think of the number, I think there's about 135 or so NOAA co-op sites throughout the region. We filtered these, we got daily mean air temperatures, we filtered them for QA, we got rid of sites that were missing too much data. We screened them using land cover data to make sure to the degree possible that we're away from urban areas, all those types of things. And then we looked at the signature of these events in the MODIS time series at each of these locations. All right, so here's what the temperature anomalies, just to give you a little bit more of a sense of this, look like in each of these years. Top panel 2010, bottom panel 2012. All right, so and what I'm showing you is daily mean temperature anomalies in 2010, 2012 relative to 30-year means based on 1970 to 1999. Okay? And so what you can see, the first thing is obviously there's a lot more red than blue, right? Positive anomaly, very warm years. And just for reference, the vertical black lines, those are the months. So the January, February, March, April, May, June. Okay? Am I allowed to touch this screen? You're not going to get mad at me, your new screen. And so you can see a couple of things here. One, a lot of red. Two, you can see if the scale, the axes are slightly different, right? So we're looking at, in 2012, days that were consistently 5 to 15 degrees warmer than average in certain periods. And then the last thing I'll point out is that there's a subtle difference here, but it's important, which is in 2012, a lot of the warmth was front-loaded. Right? It was still warmer, but the big warmth came in March as opposed to 2010, where it came a little bit later. Okay, so the timing is actually important here. All right, so what we're going to do is this very simple analysis. This is giving Sandram bad flashbacks, right, to his days working with me. We're going to use MODIS, and so this is just sort of a very qualitative description. Here's MODIS EVI in January, March, April, June, and so what you can see is as we go from winter through spring, we have the green wave at 8-day time intervals, and we take the data at each pixel, each 500 meter pixel, we fit a logistic function, which is widely used, commonly used type of representation for biological growth processes. We then have a continuous function where we actually look at the rate of change in curvature, which is similar to but not identical to the second derivative, and that gives us an objective basis looking at the maximum rates of change for pegging the start of the growing season and when we sort of hit maximum leaf area. Right? So we're going to use these dates from those data to look at the timing. All right, so here's just a really simple sort of qualitative description of that. Starting on the bottom panel, this growing degree days. All right, so the blue line, is the long-term mean. And so the first thing you can see is red is 2012, green is 2010, and you can see how much warmer we are starting in, this is around March 1st right here. But you can also see 2012 warms up early and then goes flat, while 2010 warms up early but really has its steep rise later on. And then what we see in the MODIS data, all right, so these are anomalies in the MODIS observations at each of those sites for each of our 8-day periods across the spring. You can see relative to the other years in the record, substantial, statistically significant anomalies, but more so in 2010 than in 2012. Right? So we're seeing greener, and we're seeing greener earlier in response to those anomalies. And then in terms of the timing, right, so these are box plots showing you for each year across, I forgot to mention, there's 79 sites that we included after we did our filtering. Here's the distribution for the start of spring across those 79 sites in each year. And you can see 2010 way down there. It's like 12 days to 2 weeks earlier. And then 2012, similar, but not quite, but 9 days earlier. Okay, so it's a short record, but it's a pretty strong signature for those 2 years. Oops, that slides did not come out. Whoops. Okay, so what I'm showing you here, this should say latitude, that should say longitude. Apologize, little Mac PC issue here. What I'm showing you is the magnitude of the anomalies at each of these sites. The red circles without the outlines are 2012. The black circles are 2010. And probably more sort of relevantly here, this is the distribution in each of these years. So what we can see is that there's a median anomaly of about 100 growing degree days in 2010 on May 1st, which is about the time that leaves typically come out in New England, and 150 growing degree days in 2012. All right, and so one of the things that's sort of striking about this is that on average, based on the base temperature and the starting date that I'm using here, it's about 200, 220 growing degree days before leaves start to pop. Okay, so what this is saying is that in 2010 or 2012, when the leaves came out, in a normal year, they would only be about halfway towards meeting those thermal requirements. So it's a big anomaly. All right, and then so sort of translating this into the sort of the units and the scale I'd already talked about. All right, so here's the anomaly in the timing versus the anomaly in the growing degree days, the thermal forcing. We only have 12 years here, so I'm a little bit reluctant to put too much credence on sort of linear models that fit these guys. But you can see a couple of things here. One is, at a minimum, right, the data are pretty much in the right quadrant, right? So at least cooler, later, warmer, earlier. And you can also see how different 2010 and 2012 actually are. I mean, they're way out here on this scale. All right, and then the other thing that I think is quite important here is that there is not a lot of evidence, certainly in 2010, that there's any kind of asymptotic behavior, right? In the sense that there's a lot of theory out there related to the behavior of hardwood species in terms of their response to warming versus photoperiod. What are the controls that actually influence the timing of phenology? So is it just temperature or some of these other things coming in? There's no indication here that there's a lot of sensitivity, at least in these data, to other controls. The temperature is really driving the story here. And then the last thing is that even though you can see 2012, it's a little bit further out on the scale, is warmer, 2010 was earlier. And so that's the last question on this part of this talk, is what's going on there? And the answer is it relates to what I referred to earlier, which is the timing question. All right, so this is kind of not an entirely intuitive figure, so let me just walk you through this. What I've done here is I've taken each of those sites that are included in the analysis, and I've scaled the data relative to the date of greenness onset. All right, so this is the number of days at each location before things greened up, and then this is the total proportion at each site of the thermal forcing required to green up. All right, so what's the story here? The blue line is 2010, the red line is 2012. What we can see is they both start out kind of slow. 2010 is actually relatively average relative to the other years in the record. And what we see here is about 50% of the total forcing required for green up happens in the last 12 days to 2 weeks in 2010. Versus 2012, we see half of the forcing actually happened 3 to 4 weeks before green up, and then it just slowed down. All right? And so, ostensibly, the story here is that timing matters. It's not just the total amount of thermal forcing, it's actually when the thermal forcing happens, and that this last couple of weeks is much more important than earlier in the period, which is kind of an intuitive result. It's not a surprising result, but the models don't have this in them right now. All right, most of them are just basic total growing degree day models, so we clearly need to address this. All right, so far I've showed you MODIS data and some data at co-op sites throughout the northeastern United States. What I'm going to do now is I'm going to transition to a couple of ground-based sites. So for those of you that are not familiar with the geography here, here's Boston. We're going to be looking at Harvard Forest, which is in north-central Massachusetts, about 70 miles east of Boston, and the Hubbard Brook, about 100, 120 miles north of Boston, two kind of iconic LTER sites. All right, so here's a slide showing you just the trends in temperature during the springtime at each of these sites, based on measurements that are collected there, and that they have met stations there. And I was expecting to see warming, but I was quite surprised at the magnitude. So what I'm plotting here are mean daily temperatures for the period March 15th to May 15th, nominal springtime in New England. And what we can see is the same types of patterns at each of these sites, and anywhere from about 0.4 to, what does it say, 0.5 degrees per decade. So over the last 50 years, springtimes have warmed by about 2.5 degrees in the northeastern United States. And as I said, I was expecting to see warming, but not this much warming. That's pretty pronounced. All right. So then the other dimension to this is that if we now start converting this into units that I've already discussed, which are what plants are sensitive to, this notion of growing degree days. Growing degree days are cumulative, right? So if you warm by 1 degree, then that's accumulating over the entire period. So what we see here is that Harvard Forest, we're now looking at a trend, or Hubbard Brook, of anywhere from 13 to 16 growing degree days per decade. All right, or this is kind of an important point, over the entire 50-year period, an increase of roughly 75 growing degree days during the spring. And the reason why this is important, or I think is significant, is because if you compare that number to the number I just gave you for 2010 and 2012, right, which was 100, 150 growing degree days in a single year, what that's saying is that those unusual events are twice as large as the entire change we've seen over a 50-year period. All right, so those events are pretty darn unusual, but we've still seen quite a bit of change over the last 50 years. All right, so the question then is, what are the trees doing? All right, so here's the trend, linear trend, at Hubbard Brook and Harvard Forest over that 20-odd year period. for which we have observations, and we get a trend of about 2.5 days earlier spring per decade. Okay, not statistically significant, but that's a hard thing to do with such a short record, and data which I've already described vary a lot from year to year. If we convert that to the units I've already described, which is what's the sort of the sensitivity, bud break, the timing and bud break anomaly relative to the anomaly in growing degree days, we see a similar but even stronger relationship to what we saw with Modus, partly because we've got a longer record, but again, about 11 days for every 100 growing degree day increase earlier. Okay? And a pretty nice sort of tight relationship, and again, with very little evidence that there's any kind of asymptotic behavior at either end of the scale. Okay? So we've done Modus. We saw one trend about 8 days for 100 growing degree days in terms of sensitivity. We looked at the ground data. That's showing us even steeper, around 10, 11 days. Now I want to take a step back and actually look at Landsat data and talk about how we're using that to look at dynamics and phenology. All right, so this is work that my PhD student Eli Melas has been doing over the last few years, where he's looking at Landsat data. And when Eli first came to me and said he wanted to try this, I actually didn't think he could. How are you going to do phenology from Landsat? The temporal sampling is too dense. But what Eli did was he came up with kind of a clever way to do this. All right, so what I'm showing you here is sort of a basic description of the way he approaches this. This is for a single pixel at the Harvard forest. All right, and so what he's done is for any given pixel, you take the entire Landsat time series on order 500 images over Harvard forest over 30 years, and you just plot every observation relative to day of year. Okay? And then based on that, you can fit logistic functions for the spring, logistic functions for the fall, and what that gives you is a mean phenological profile for the year at a given pixel. Okay, so we've got the mean now, and then based on that, if you assume the slope, which is, it's an assumption, but it seems to be relatively robust, that the slope is kind of consistent in any given year, so you might shift forward or back, but the slope's going to stay consistent. The horizontal anomaly here gives you the anomaly in any given year. All right, so that allows us, we've now got the mean, we back out the anomaly in each given year, and you can get the phenology at each pixel in any given year for the timing of spring and fall. So that's it, that's the whole method. So here I'm just showing you, just by way of illustration, this is a 6-scene Landsat mosaic for the northeastern United States, showing the mean timing of phenology over the 25 to 30 year record that we have based on Landsat data. And if you zoom in, it's actually quite remarkable, the level of landscape detail. I'm used to looking at Modus, right? So looking at sort of landscape detail from Landsat, it's really quite powerful. Here's the Green Mountains in Vermont, here's White Mountains in New Hampshire. You can see the Cape and the Islands out here off of Boston or later because they're out, got a strong maritime effect and so on. It really works quite beautifully. All right, so just, the first thing to do here is just a bit of a sanity check. So what I'm showing you here are the anomalies in Landsat relative to the anomalies from Harvard Forest and Hubbard Brook that I just showed you. And you can see they kind of line up beautifully. So it's really, all indications are is that this method is working really, really nicely and is actually giving us good, reliable data related to the timing of phenology, which is really, it does two things. It expands our record backwards in time relative to the ground measurements, and it also allows us to extrapolate from 2 sites where we've got ground measurements in New England to basically the entire region. All right, so then, my postdoc, Josh, actually sort of said to me that one of the problems with this presentation is you see the same plot over and over and over again, which is kind of true, but it's also kind of the point, right? We're seeing the same patterns in all the data. So here is the trends in the start of season from the Landsat data at Harvard Forest and Hubbard Brook. And again, we see the same kind of thing, about 2.5 to 3 days per decade, but again, not statistically significant. Hubbard Brook we do, but I think it's partly because we've got this one guy up here, which has got a little bit too much leverage and increases the slope a little bit. If you took this data point out, I think the p-value would go up significantly. And then here is the quote-unquote sensitivity, the response and the timing, the anomalies, the timing relative to the anomalies. All right, and we get the same type of result that we saw from MODIS and the ground data on order 10, 11, 12 days for every 100 growing degree days. All right, so it's the same story across these different data sets. So where does that leave us? If you look at available projections for the northeastern United States, which is the part of the world I'm kind of looking at, you're basically looking at on order 3 to 5 degrees warming over the next 50, 70 years. All right, so these are the blue dots and the red dots are downscaled AR4 climate projections for the region. The green lines are some simulations that I've done. I won't go into details, but the main point here is that if you do a back of the envelope estimation based on the sensitivities I've already characterized throughout this talk and this level of warming, we're looking at 2 weeks to 3 weeks earlier springs in New England by the end of the century. And that's on top of 8 to 10 days of earlier spring that's happened in the last 50 years, which is a really remarkable change. We're just talking about the spring. There's lots of evidence, although it's harder, that the same type of things are happening in the fall. So by the end of the century, we're looking at a scenario where in the northeastern United States, growing seasons are anywhere from 30 to 50% longer than they were 50 years ago, which is a profound change in the land and sort of ecological system there. All right, so back to the big picture. The implication here is that clearly what we're seeing in New England is not just happening in New England, but elsewhere, and that at least part of that is driving this increase in the amplitude. Right? Longer growing seasons, more intense growing seasons, and that's driving increased amplitude in atmospheric CO2 on an annual basis. All right, and we've got lots of evidence. This was a paper by Alan Zhu and Ranga Mainetti and a bunch of other co-authors at BU showing that showed up in Nature Climate Change a year or so ago that clearly showed, at least from remote sensing, that things are greening up at higher latitudes in response to climate change. All right, I think it's pretty unequivocal at this point this is happening. The sort of the missing link here is how does that actually translate into things like, I mean, there's lots of questions, right? Ecological questions, but the one question that everyone wants to know is how does that translate into carbon budgets? All right, so these are some results from work that we did with Trevor Keenan as the lead author on it that's in press now at Nature Climate Change, where what he did was he looked at the northeastern United States larger, the temperate force of the eastern United States, looked at 7 different flux towers, looked at trends we see in the MODIS. We see the same types of patterns that I've looked at up here throughout the northeastern United States, going to earlier springs over a relatively short record. And then this is corresponding, it's a bit noisy, but the signal's still there, changes in the sort of the net uptake period by the forests at each of these flux towers. And what we see is indeed, some more so than others, particularly at Harvard Forest tends to be quite strong, we're getting more uptake by virtue of these longer growing seasons. All right, so there's a sort of a consistent story here, but there's one last wrinkle I want to throw in here, which is something that my postdoc Josh has been working on, which I think is actually really, really interesting, which is that most people are focusing on natural ecosystems. Right? It's a natural idea, right? That says you look at an image like this, and it's like, boy, the high latitudes are just greening up, and that's what's driving all this. And that's probably true, but there's other stuff going on as well. And one of those things is human activity. All right. So what I'm showing you here is changes. It's really quite remarkable. Changes in agricultural productivity over the last 50 years. So, and this is changes in production, teragrams for every 1 degree grid cell, and you can see Midwestern United States, North China Plain, Indo-Gangetic Plain, enormous increases in productivity. If you go, your typical cornfield in Iowa has gone from 50 bushels an acre to close to 200 bushels an acre over the last 50 years. And what that means is a lot more carbon being pulled down in these concentrated areas. And so what this is showing you is the change in seasonality, right? Because agriculture is basically net zero in terms of its carbon budgets. We grow them, we take the food, most of it actually goes to livestock, right? And then it gets respired back out. Right, so we built a simple model to calculate seasonality. So we've gone from about 20% of a teragram to 0.2 teragrams to about 0.8, 0.9 teragrams increase in the seasonality just from crops. And perhaps most remarkably, this is breaking it out by crop type and by region. The vast majority of it is in the United States and China, and 2/3 of it is one crop, which is corn. So, so our net, what our back of the envelope estimate is that this is explaining roughly 25% of this change, which I think is kind of a remarkable result. So we're just trying to finish up writing it up right now, but I'm pretty excited about it. All right, so I'll stop there. What's my take-home story? Warming throughout the northern hemisphere is obviously happening in the northeastern United States. We've seen about a 2.5 degree warming, which corresponds to about 75 growing degree days over the last 50 years during spring. Trends all point towards earlier spring. I don't think there's any surprise. We've seen about an 8 to 10 day change over the last 50 years. But one of the main things here that I'm trying to hammer home is that it's not just trends, it's interannual variability. That's where the information is, right? So we're getting year-to-year variability that's larger than the long-term trends, and so that gives us sort of an opportunity to look at these sensitivities a little bit more carefully. We see this sort of consistent story across data sets of about 10 days for every 100 growing degree days, which implies moving forward at least a 2 to 3 week change in the start of the season. And then lastly, these have, among other things, there's lots of ecological implications, interactions across trophic levels, there's lots of things that are happening here. Ecosystem, changes in community composition, but there's big implications here with respect to, or potentially big implications with respect to carbon budgets, but land use activity by humans. That's not the only story. Humans are part of the story here too. All right, so I think that's it. Yep. Thanks for your attention. I'll stop there. Happy to answer any questions.